this microphone's on, right?
Yes.
And you got to wait. This allegedly is going to turn on. Here we go. Okay. Well, thanks for the very kind introduction, and especially Professor Seneca before. That was what a great setup actually to what I'd like to talk about here, because it's not going to be about supercomputing at all. In fact, if you're from the computer science side, a lot of the terms I'm going to use, the things I'm going to talk about, might be a little strange, right? I'm talking a lot about economics, a lot about things like service contracts and value chains, strange things like that. But it is actually, I think, really part and parcel of pulling off this revolution, and it is one, right? And we are living in and driving it this year. It was the three great ones, of the agrarian to the industrial to informational, and a lot of people kind of ask me, say, do you think that like the internet is overhyped or whatever? And I keep responding, no, it's completely underhyped. You really don't know what's going to happen. And that's actually part of it, right? Nobody really knows what's going to happen. And one of the most difficult things is to understand and really internalize a revolution when you're in the middle of it, right? And we're in the middle of one. And I mean, I'm really excited about what's going on here in this center, and the whole focus that is into the internet technologies. And I think as that will really grow to be something about what does this informational age look like, and what really is the substrate? What does it take to pull all this off? And that's what I'd like to focus on, and I'm going to take a piece of it, okay? And sort of the piece of it that I hope will give some stimulation, maybe some challenges here, is one of scale, okay? And I don't think well, I can tell you from the industrial side and wrestling with the problems you're going to see here, that we really understand much of anything about really large-scale computing. And I mean large-scale, and the words I'll start to use it here are things like very predictable and available and dependable, and what does all of that mean, okay? Now, before I launch into this, just to sort of give you a sense of motivation of why I even drill into this, is that in my experience as to what if I were to try to distill down the number one issue or concern that drives people who are trying to use computing today, right? What really are the barriers, both to Wall Street, lots of people, right, or to manufacturing companies, or to wherever? They put on the top of the list is complexity, right? What has really happened is that we sort of accreted a lot of functionality and pieces and networks and computing and software development techniques and all that, and it mostly works, right? The problem is I don't think it works at the scale we need it to work at, and that's the fundamental challenge. And the complexity becomes overwhelming because applications that we used to think of running on a single machine are now spread over a network. And when something goes wrong, you don't know where or why, all right? I mean, we really have very little observability of this beast that we've created, and I would say, very shallow understanding of what's going on. So I think if you lead with anything here, it is, always come back to think about, how do you attack the complexity as things scale, because you don't get scalable systems unless you can scale without adding complexity to them. I think that's the key. So let me dive in then to this particular aspect of the problem, which is really about building up the infrastructure. So the big vision, and I've sort of there's enough setup of this about what maybe the wired marketplace might be, and I'll say a few more words about that. But the profound impact really here, I think, is going to be an economic one. And it's not that, remember in informational age, manufacturing doesn't go away, just like manufacturing or industrial age, agriculture didn't go away. It's just different, and it's integrated in a different way. You know, at a technology level, you can treat this as, well, this is something about the bandwidth revolution, right? And things becoming cheap in bandwidth, and we've gone through what the decade of the integrated circuits and cheap microprocessors, and now it's really finishing up this sort of tremendous growth in optical and lasing technology that's created this bandwidth wealth that we're starting to see companies harvest. Or the final one, and another way to look at all of what's happening and why I think this is a technology inflection point, is that, you know, again, where we've been is sort of the computing being embedded sort of everywhere. And maybe the 20 million systems that we identify as computers today that, say, were shipped last year, there were, you know, hundreds and hundreds of millions of things that were microprocessors, right? That you wouldn't identify as a computer, but were running code and doing it, right? All the way down to, as Danny Hillis' famous remark about microprocessors being in every doorknob, right? And having spent a good part of my life, the last 3 years in hotel rooms, I can testify. And you know, so it's sort of like microprocessors are really everywhere now. And the other way you think about this is that, well, what happens when all those microprocessors that we put everywhere have a network connection? Right? And so I'm not, when I think about things in this way, it's the billions and billions here is not computers that we would identify, but it's in fact sort of the intelligence and the fabric. And that's both, you know, input and output. I think if you follow some of the futurists in these areas, like Paul Sappho, he would say that the next generation that we're into now, after gone through the microprocessor transistor revolution, the bandwidth revolution, the one that we're perched on the edge of now is the sensor revolution, and how we're going to really be integrating sensing and affecting into our computing systems. Because really, computing systems are dumb today when you get down to it, right? I mean, my laptop here is waiting for me to press a key, right? And if I got hit by an asteroid right now, right, and disappeared, it would still be waiting there for me to press the key, not know that anything changed. So that may be something to think about, but is the result here. So I'd like you to think about the challenge here is really sort of these billions of devices, right? Be a little Sagan-esque here, right? Billions and billions. And I got to push you to that kind of asymptotic scale, because if I don't, you won't fundamentally deal with the complexity issue that underlies that statement. And when I say that, actually the attributes that I want, most importantly, is predictably. Okay? So here's kind of a term we don't throw around too much in computer science, but predictably is, well, it's available, right, that I can get to things. But if I'm talking about a service, let's just say, you know, in a traditional way, like getting to a web page or my email, or something like that I not only want that service to be available, right, that it's there for some, you know, time fraction of the time that I would want to demand it, but it's predictable that I get acceptable response time, right? This is hard, right? We really don't know much about the science of predictability, as it turns out. It's particularly in network systems. Securely, right, key. It all falls apart, right? This whole sharing thing that we created really sort of gets very destructive unless we can solve the security problem, and of course globally, right? And these are really sort of the points of you know, you really get the location independence, and you see a lot of people now writing about sort of the things like the depth of distance, right, and what that means. Now, I give you a bit of a feeling of magnitude in case you think that this is a small change. That if you just look at global telecom in the year 2000, that's like $1 trillion market. And that's just, you know, voice and data service. That's a couple $100 billion in equipment. People like Lucent, you know, $800 billion in services, folks like AT&T and the like. So the premise of this talk, you know, it sort of focuses in and maybe give you a flavor of the kind of thinking that I'm talking about, and actually pull an example out in the area of just wireless and low bandwidth connectivity. That we really have to move our concept, I think, of networking from just being a connectivity contract to one that is more about providing services, right? And how do we How do we go through that transition? So I'm going to give you a few different views of that. One view is that if we look at the stacks of systems today and how we treat them, we really have these sort of devices. There's a network, set of services that connect to that network, and maybe content that sits on top of that. We view these layers as pretty distinct, with a set of well-defined contracts in between. For instance, this has really become TCP/IP between this level and connectivity around the connectivity cloud. One way of sort of interpreting the premise I'm going to say here is that we really have to treat the services we're providing in the connectivity, the fabric, as sort of one problem, right? And that problem, and this is sort of like marketing language that we're using these days, but trying to give an icon for the services that this whole global information infrastructure or utility, right? Another way to think about it, will provide is we call web tone, and that's sort of to try to take off the dial tone, right? Dial tone is this, you go plug the phone into the wall and you pick it up, you get dial tone. That's really, it's not a service. Dial tone isn't a service, but it's sort of an icon for the availability of a service. You have pretty high assurance you can type in a number and get connected to something, right? So that's really what is the equivalent of being able to roam around with a wireless system or plug into an RJ45 in the wall and get to your network services. So that's one way. Okay, here's another way. It's sort of stated a little bit differently. But if you look at our view today, we have, we start with these clouds, right? And by the way, all great system design these days is network-centric design. You start with your network and you make sure that's as good as you can build it, and then you worry about the stuff around it. And so if you start to worry about it, you build these clients, build servers. Of course, this has moved to multi-layer computing, so it's server, all kinds of discussions there. But the contract that I have, right, this is the connectivity contract, TCP/IP packets. I name things using IP addresses at that level. And most importantly, this last point is that the promise that I have from this fabric, right, the service level I get from that fabric is a best effort contract with TCP/IP, right? You throw the packet in the network, and it will get there. In fact, if you look at it from a predictability point of view, this is both blessing and the curse of what we've done with networking, because our networking is in fact really good at getting packets there, even when there's something terribly wrong in the connectivity. We may not see that or know exactly where it's wrong, but it gets delivered, but it may not be at the response rate that I actually need to enjoy it. So if you want to look at it from this point of view, the view tomorrow is that connectivity cloud changes to a services cloud. And again, think utility here, think global, secure, etc. And then the contract that I want with that utility is about a service protocol. I want my mail. I want to do some conferencing, messaging, right? I want to do an economic transaction, right? So what is that? What are the service protocols we want? I don't know them all, right? I'm just giving you some that we're pulling out of how we think about things today. But what's this framework for describing service protocols? How do we name them? And I think actually, to me, the real revolution of the web was the URL, right? This HTTP://www, right? That is fabulous. A string of characters that I can take anywhere in the world, completely location independent, and identify a piece of data or an application. And that's profound. That's better than the worldwide telecommunications business, right? Where you go to some other country, you got to know what codes to type to get out of that local fabric. And then most importantly here is this concept of service level. All right, how do I think about, and this is a hard problem, not just from being able to promise a service level and give the mechanisms for providing it. Right, I want this response time, I want this availability, I want this quality, I want this security. But it's also, and you got to deal with it, how do I pay for it? How do I charge for it? How do I account for it? How do I authenticate people should get what level of service for what kind of applications? What are the policies that go with that? Right. So, one of the consequences of this is that where we had, I believe, and maybe this is controversial to networking people, is that where we thought about this sort of clean interface between connectivity and computing, that we won't, those distinctions are going to work. that we will be using the computing tools to integrate into the network to get the qualities that we need out of the network to provide those services. So I'm giving some examples here, right? And I'm going to take a piece of this problem and sort of develop a couple of examples, what I'm calling proxy and caching. Okay? But there are all other things of how I manage the namespace. I was talking about policies, security, authentication. Oh, this can go on for a long time. So let me make a remark about the science behind all this stuff, because in many ways it's a plea for help. It's why having centers like this, and if I can influence at all sort of people's interest and directions here, it's this. I think telecom services, we can more or less do it at any scale, right? If you're in China right now, you could be acquiring a regional Bell operating company and building that infrastructure about every 6 months or something. Great, if they're building a phone system, you just order it. I've got 50 million people here, give me a phone system, right? Can you do that with information technology? I've got a 50 million person sort of, environment that I want to supply information technology to. I don't think so. I really think we're pretty clueless. We've got to the point where we've got pieces that do compose across the interfaces I showed before, and most of them work. Right? That actually turns out, the ubiquity of that turns out to be really important because it was good enough to get this whole thing bootstrapped. But I think if we can't follow through on the promise of some of these higher standards that I'm talking about here, I'm not sure we're going to really see all the benefits that we're imagining. Okay, so here's sort of that's the setup. Let me give you the outline for where it's going to go from here. I want to make a comment about technology cycles in the business because that's actually something that also has changed profoundly. Okay? Of how technology sort of gets created and reinforced. Something about what this means, why I think networking gets sort of exposed to some problems. And I'm going to take an example and dive into some technical depth here about how do you deal with sort of intermittently connected devices. And then sort of speculate about, well, just, how far does this thing go? Okay. So here's this technology cycle, and I'm drawing this, I'm starting this technology cycle discussion. How is technology sort of created, at least an important aspect of it today? And, here I start with clouds, internet and intranet, and, internet being the sort of what's behind someone's firewall, and what's in their campus. It's using internet technologies to support information architectures inside enterprises or institutions. All right, so you know that distinction. Public behind the firewall, I think, is the way we talk about it today. But I'm going to go through this discussion of this. It's very different. Starting with technology. I'm a technologist, right? If I gave this talk 3 years ago, I would give a very different sort of view. I'm going to start with networking as the center of talking about technology, right? We get into what kind of discussions were we having 3-4 years ago? Right? Risk versus CISC. That's the names, right? CMOS versus bipolar. What?
RAID versus SLAM.
Yep. C versus COBOL. Multi-processing versus uniprocessing. And what's fascinating me, you want to see rate of change? All that stuff is really uninteresting. I mean, truly, profoundly uninteresting. Because, well, actually, I think they've all been answered. So you look at it like risk versus CISC, we found out that was the wrong question, right? That it turned out to be a lot more about coupling people's ability to execute well around an architecture as a business and the whole relationships to building critical mass with software. And I use the extreme points there of probably the best microprocessor architecture on the planet, DEC Alpha, right? Really challenged from an execution point of view, all the way to the point of DEC being required. Who would have imagined that? And then the other extreme is Intel, right? I think most architects like myself would put the x86 family in the brain dead category. But what fabulous execution by that company, right? Who would have guessed? In the middle of our debates about the technology differences between CISC and RISC, that Intel could have done just such a stellar job. that CISC architecture. I can pick a few of those other ones out. One of my favorites is the C versus COBOL kind of debate, right? And I like that one because that one gets determined, right? January 1st, 00. We know that, right? I predict COBOL programmers will be arrested on that. Society, we demand to blame people to know, and if you'd like a discussion sometime, I can tell you where you should not be in the year 2000. But actually, on a serious note there, and I'll make another comment to it, is that where we're scared is not that we can't have, for instance, our business year 2005, which we think that we have that under control. But it's all the businesses we depend upon. So if one of our suppliers goes down because they just lost it in their information systems, we're screwed. Okay? We can't build things because we get these very intimate supplier relationships. I'll talk about this. So back to this cycle. What you see today, if you want to get really base about it, is that the business model today, and a company like Netscape really pioneered this model, is that this is where you give stuff away, and that's where you make money, or you hope to make money, right? And the giving away here is really interesting, right? You throw stuff out on the internet for free. Now you get source code for free, right? And you do that, why? Because you want to build, you need to build critical mass for your technology. You need to build brand, is really what's going on, demand for it. And if you're lucky, what happens, and you've done this right, you become one of the winners that comes over here that people will pay for, okay? But there are many more losers, right? How many different styles of streaming video content on the internet today? How many should there be? So what happens is that a lot of people are going to try, and you become a winner. You can build a business around it. You can try to get acquired for your technology, but because it supplies something that people will pay for to be what? More predictable, robust, reliable in this space. Right? So if you look at that and what's happening today is that a lot of things have made the transition. So this is TCP/IP, it's HTML, HTTP, Java, all those. There's a number of core technologies made across, and people are building internal applications around that and actually enjoying some very interesting sort of complexity reductions by doing that, right? I mean, coming back to the complexity issue, one thing that the web has done for internal application design inside companies is it's completely settled the user interface debate. It used to be a raging debate, right? People had staffs of people working on user interfaces and deciding what it should look like. We know what it should look like. It should look like a browser, stupid, right? It's point and click and all that, right? So it's really fascinating what's happened there. But I'll tell you, the part that is the reinforcing cycle that we're just starting to get into is where now I can take this sort of hardened technology and deploy it externally and really start to integrate, get close to the customer, and integrate my supply and distribution chains as a company. That's actually key. All right, and this is really where when you get outside of the corporation, where these are arguments about efficiency, perhaps, of implementing my information architectures inside a business. This is about the way I conduct my business and how I reach people. So, an example may be, if you call your financial institution, you talk to somebody at the end of the phone, they're in a call center, and actually call centers are very, very sophisticated beasts, as it turns out. But somebody in a call center will, say at a bank, will try to get access to, your mortgage, your account balances, your credit cards, investments, whatever it is. What happens actually today, those are really on disparate systems. Okay, and at the call center, they're trying to bring all that together and help the person hop from point to point, give you sort of a feeling of, I've got a single relationship with this bank. Well, a lot of call centers have been re-engineered around web technologies. That's a big trend now. Okay, because once I can do that, right, then I can take that application or some purified subset of it and give it to you directly, and now you have home banking, right? I can give you a closer relationship than I have before. So Let me come back to this supply and distribution cycle because I think this is really at the heart of why this becomes a revolution. All right. So I'm giving you a very simplified model here, trying to show you like how a company like Sun, as a manufacturing company, how we sort of sit. This is very highly abstracted, but we have all of these chains coming in as suppliers, for our components and subsystems and all that. And these supply chains, of course, can get very deep. So you can imagine, like, we buy a disk drive from someone, and, where did all the components for the disks come from? And those will go through, distributors who will do aggregation and all kinds of functions for you. And then you consume those as a manufacturing company. You hold some of these things as inventory. You build your products, and then you look for the backside, which is your channels, okay, of how to get the product out, right? And the channels are one of the most interesting challenges here. There are a number of different models. You go through resellers, value-added resellers, you have direct sales forces, go to distributors and dealers and retailers. For instance, Sun really balances the business between these two distribution models. Now, if you look at this, what happens with the network and sort of broadly electronic commerce as a result of this cycle playing out is that a lot of these intermediaries are probably going to go away because they don't make much sense. Right? And you can re-intermediate them, so to speak, with electronic relationships. So a distributor, what's a warehouse? To me, that's a FIFO, right? What is it doing? It's just kind of adding delay and cost and latency to the system. And so you can sort of challenge various aspects of this model and see where you end up from sort of an efficiency point of view. Okay, so what can you take away and then put back with using the network? So let me give you some examples of that. Amazon.com, people order from there, right? And you can look at that and say, well, Amazon.com just totally nuked the whole bottom end of that distribution, right? They just said, you just go to our website and order from there. And you might think of that as a model then that's challenging sort of the costs, in fact, and maybe even availability issues of things like Barnes & Noble or Big Alton Bookfront, retail point of presence. But that's one side of it, but I actually think more profound about Amazon.com and their secret sauce, I believe, is the relationship that Amazon.com has with the book publishers and book distributors, right? In very efficient ways to aggregate your order and get them through the transportation system to deliver to you. That's interesting, right? If you look at things like Dell, Dell has made an incredible impression on the computer business because what Dell did was said, you see all the distribution stuff down there, with these retailers and VARs and master resellers, that's all over here. You're all gone, all right? You order from us. And we'll be good enough with our information technology that you order a specific configuration, just a one-of, we'll make sure it gets built to your specification efficiently, right? The other thing they do is that they're really ruthless about their supply and distribution. They basically carry very little inventory, so they have a very efficient economic model. But Dell has really, really changed the computing business. And why have they changed it? It's not because they make machines. Their machines are identical to everybody else's. Somebody from Dell would not agree with that, right? but they're basically identical, right? These are commodities, right? But they do $3 or $4 million a day through their website. Became ordering system, goods. Okay? Of course, this is very natural to do things like you better be secure and predictable, reliable with that. Auto by Tel. Has anybody bought a car through the internet? I did. My wife kind of thinks that was taking my job a little too seriously today. It worked great. It was a great experience. I won't do it any other way. In fact, what happened is that in ordering this car, and you go through a bid process, basically, and we ended up getting this for dealer transfer cost. All right, so we went into the system as if we were a dealer, right? We basically disintermediate the whole retail side of the auto business, and when we went to pick up the car, we had explicit instructions. So we went to the dealer where we were going to pick up the actual good. That he said, do not go to the sales floor. You go up to the fleet department, and it was actually a very pleasant transaction. It was like 30 minutes, write a check, they give you the keys, you go. And so, after that, I was off in Detroit, and I said to people, I did this, I enjoyed it, but I really screwed you because I, of course, went and drove the car. I went to a retail place, and pretended like I was going to buy them for a salesperson. All the time I knew I was just checking out the car and go buy it right away. And I said that, isn't it going to give you a lot of problems? And they said, well, no, it turns out that in their studies of consumer behavior at auto showrooms, is that about 90% of their automobiles are purchased on impulse. Well, people mostly know they're in there because they want to buy a car, but they really haven't done any comparison shopping or anything like that. They see something, they like it, they want it, how much per month? Really interesting business. I had some remarks down here about things like the amount of business done through the web, and $97.5 billion. Boy, that's old because, Dell alone is clicking along at $1 billion. Cisco is a couple $1 billion through the web. And then advertising in '97 was all around 800 million. Viewing to be 4 billion this year. Okay, there are actually people making like CNN Interactive is a real money-making site. They get very big ad revenue through it. 4 billion is very small compared to television, but that's about the size of radio advertising. Interesting. Okay, so if you look actually at the other thing is the sort of the goods and services that are part of this people building the internet and building their intranets inside companies, you got to take a lot of these numbers with a real grain of salt. Mostly people who look at this stuff, are just guessing, but it's a guess relative to their other guesses, and that's the interesting factlet here. In '96, guessing that about $20 billion, in the year 2000, maybe shy of $100 billion. But according to Mrs. IDC, they think this is a 50% compound annual growth rate, or 5 times the total IT growth rate. Right? So they attribute this as the driver in information technology over the next few years. Actually, I don't think that's entirely correct. In my experience, the big driver right now is the year 2000 problem. It is amazing what's happening there. So, here's a view of, I think, some real trends here, is that if you look at this model, the distinction between internal and external is going to erode. This is really an artificial view that we have an outside thing and then a secure inside thing. Important to some of the more technical side I'm going to get into here in a minute is that the spectrum of clients increases dramatically, and the disparities in bandwidth among those clients grow. So it's not, we have lots of bandwidth, but we're really just increasing the dynamic range of the bandwidth that's available. And I think that has this consequences back to my first theme, that this is going to be a service model when we get done with it. So the turning inside out, there are all these pressures that you can see that you want to penetrate firewalls. We've discussed really a lot of these. There's also internal pressures that you want, is you can, with enabling, you share data, you may be sharing too much, right? Who here should see student records? Even though those may be on your intranet. The other thing about this client becoming appliances, this is where you get to the billions and billions, right? From the sort of tens to 100 millions kind of things through devices that are smaller and smaller, but fundamentally have network connections. In fact, if you look at some of these things, what's a net TV or a cell phone without a network? Voting, right? Nobody cares about it. And, I'll show you. This is my favorite toy, my latest one. This is a full, two-way pager with email. Okay? And Motorola, we just finished a very broad cross-licensing with Motorola. You'll be able to load Java applets and this. This is a great toy, right? But those are the things. So how many of these am I going to have? How many of these kind of things will we have? What is the range of the number of devices that will just be kind of part of the appliances that we deal with? So I think that's a big important thing. But this bandwidth issue is, we're going to these, role of switch bandwidth, LANs and WANs, really hyper bandwidth system area networks or storage area networks, gigabyte per second kind of things. But then the importance, because all of these devices are sitting out at the leaves of this tree, right? That the importance of these so-called impoverished bandwidth devices really grows, right? So, and I think this exposes what I call networking three lies. I think there are at least three of them. These are the three that seem to underlie a lot of the assumptions of application design that I see people doing around networking, which is that, well, the bandwidth's going to be infinite, there isn't going to be any latency, and there won't be any errors. And people design applications that way, and you know, the sad part is that TCP/IP is just good enough that it mostly allows you to write an application in this naive way, and it mostly works, certainly in the LAN environment. Sometimes people wide area environments, but not at this step. So what I like to do is just, for kind of drilling down here, is use this distinction then of something that I'll call the well-connected internet. Right? And this is where we have all the great bandwidth. And then things what I say are impoverished bandwidth, intermittently connected clients, right? Where all of the mass of the appliances are have to be. Okay, now latency versus bandwidth, just to make sure that we're all on the same page about this. You know, if I have a pipe here that I'm stuffing stuff through, pipe in this case, right? That the bandwidth is the size of the pipe, how big it is, and the latency is how long it is. So I can have, you know, a number of corners on that. Here are two of them. You know, low latency because it's short, high bandwidth because it's fat, right? Or, you know, very low bandwidth and high latencies, as most of us have. You know, of course, the other points are happening just as often. What happens is if you plot this out and take sort of our different pieces of communication space, I get to this sort of latency bandwidth spectrum. I think looks something like this. Now, this is a log plot, and it's over a wicked number of orders of magnitude. Okay. It's, you know, 1 second down here to 100 nanoseconds, and I'm skipping decades here on the bandwidth side, right? A kilobit per second to 100 gigabits per second. So go lay these things out in the space, and you'll find things like, well, you can look wide area networking in the, you know, few hundreds or kilobits, megabits, up to, you know, growing into the gigabit range, right? Everything is growing up as bandwidth is enabling that, see the LAN. And by the way, the latencies here are like seconds to 100 milliseconds, depending on the network. Local area networks filling in here. Let me skip this for a second. The backplanes of systems sort of pushing against the low latency, you know, what can I do in 100 nanoseconds, and pushing into the how many tens of gigabytes per second can I push through a system. And actually, you know, we end up with this problem, you know, Einstein starts having arguments with you here. So as you push this way, they really end up squirting up like that. And that's actually, if we're giving an architecture talk, it's all about that problem. That's the latency tolerance problem. What's here is that without this, you notice there's this huge hole, this big gap. And in fact, these are really responding to fill this in. You get things like I/O networking, things like fiber channel. You look at that coming in and filling this part of the space. Plus, how do we cluster and really tightly integrate machines that are close to backplane performance, but more we can assemble more easily? And there are lots of people doing that. Actually, if you looked at MPP design, it was really about trying to discover networks that fit in that space. But then sitting off to its lonesome here are these, you know, where most of the interest is, the wireless and the plain ordinary telephone service connectivity. Okay? And now, so how do we close that gap in some way? Actually, it's interesting to see, is that a positive gap or a negative gap? Okay? So I'll let you, if you get bored with what I'm going to say now and you want to think about something, is what are the constant lines across here? What do they represent? Constants of what? In that chart. So think about that. We'll show you. Okay, so let me look at this client side. So what I'm going to do is just sort of step you through. I'm going to take a little piece of this problem. I'm going to step you through and say, this makes sense in terms of putting services in the network to support this model. Okay? So we'll just do that. Let me drill through that. And so we have our impoverished connected and our well-connected things, and we want to overcome that gap. So the first observation, little leap here, is that what could be very useful is to have in this well-connected network and actually it's a well-powered network too, which is nice, right? Because power is another big issue here. Is that I'd like to have a proxy, a general-purpose computing engine, which actually acts as the proxy of this device, on the behalf of this device to the network. Okay? So I'd like to split the responsibilities where the proxy sort of deals with the device to deal with the vagaries of this connection here, and then bridges that gap, if you will, to the well-connected network. So if you want to think about it, is that it manages these clients, the intermittent connections to clients. Think of from the client point of view, right? From this device, think of the proxy that I have for this device in the network is acting on my behalf, all right, for the network side. And what it can do is do things like distill and transcode data, right? I can't, this is a quarter VGA screen. I don't want to download a 5 megabyte JPEG file that I can't see on here, right? I would like that proxy. You can take that content, distill it, transcode it, get it down into some point of view that understands what I need here. But I could go further, right? Maybe I'll do some language translation there for my needs. Maybe there'll be some security, special security I want to enforce along those links, or I want auditing for accounting purposes, or increased reliability. It will do transactions on my behalf, and I'll just synchronize state. There's a great example of this at Berkeley, which is the 50 project, somebody may be familiar with, which is really a way they built this proxy structure with in supporting their wireless work, and they said, well, let's go back to this predictability thing. What the contract that they speculate you might really want is not things about I want this amount of compression and this amount of loss, but the contract is I want to see that image in 5 seconds, and you do the compression to whatever level of throwing away bits you have to in order for me to see it in 5 seconds. I want response time. Right? So they actually are very sophisticated about it, and they'll go through the calculation of not only how long is it taking me to compress this and transmit it and not only to transmit it and decompress it, but how long it's taking me to compress it. Right? And notice that you can get these reductions, really pretty profound reductions in download time in doing that. Am I doing in time here? Okay. So here's another way to do it. The way to think about this is that really when I'm writing an application to this is that I would like the proxy to sort of custom load some piece of specific support for my client. Right? And then I'll have a piece that fits on my client. And we'll make that link between the proxy and my device. We'll try to latch up to something that's a custom link. And I speculate here I could have like my Comm pilot, with let's say a wireless connection, and it identifies itself to the network. Here's who I am, right? And how does it really identify it? It probably supplies a URL that points back to name the application, my client, sort of proxy application pair that it wants loaded in. Okay. So this is really a generalization of proxies as an application tier, as you think about multi-tiered applications. And by the way, if we had time to go develop it, there would be lots of levels of proxies, because if I wanted to go to my house, okay, I might want to put a proxy at sort of the interface between my network and my house and the network that I go to, because I want to have security perimeters, I want to have a special relationship with my devices that I don't necessarily want to export. Okay? But that proxy that I have in my house may talk to a proxy back at my service provider. All right? And those two proxies concerned are managing the link. Right? And I think you get into this general thing of wherever you see a discontinuity, right, or an impedance mismatch, or a effective change of security assumptions, that's where you're going to see some computational element come in and intermediate and interesting questions about policies. I think that's a meta observation here, right? And you can see basically, let me give you a picture of this, it'll be easier, is that, as I said, is that you can sort of now, while you may start this protocol in a very general, open way, TCP/IP, service location protocol, whatever, once I get that piece of code that I need running in my proxy and my piece of code running in my client, I can then make this link totally custom. right? And what we need, we can latch up. And I think for the consumer electronics people, this is a way for them to add value to their devices. You will get devices from, say, Sony or Motorola that are just better, okay? Because they've actually managed this relationship. Of course. You were wondering, how long would it be? So I said January. Okay, I said, I'm not allowed, I would be fired by Scott if I never But it's totally content-free overlay here is one that is suggestive that, in fact, that you start putting in things like issues of security and platform independence, et cetera, that you better have something like this to be able to sling this kind of function around, okay? Because it's your, we got datagrams and applets, right? And that's how we get the thing to be Turing complete. Right? That's okay. So the focus on the server side here. Once we've done that, you'll discover that it didn't solve your problems because this actually has a number of issues related to it. But if you come back to this single point of web presence, it really doesn't scale. I mean, you can't just put one site on the internet, and we're discovering this a lot. Go talk to people in Atlanta on CNN Interactive, you'll find that they get really very different response profiles depending whether you access CNN on this coast or you're over on the west coast, and if you're in Japan or Europe, it's a disaster, right? So how do they get out to be able to get their content closer, right, and sort of overcome some of the network distances? And then the other thing is that you do get these accumulation of latencies. You just can't speed the line here. So back to these constant lines. What's the product of latency and bandwidth? Right. Bandwidth bits per second. Latency is seconds. So it should be bits. Right. It's a number of bytes in the pipeline. And you can see why long latency pipelines. They've got a lot of stuff. That we say that you have to fill the pipeline. You need to have sort of parallel activity or something in order to be able to fill that pipeline with data. But what happens when I get to high bandwidth? The pipeline gets wide and the problem gets worse. Okay, so in fact, from a high bandwidth point of view, you don't solve this problem. The problem is actually much more acute. So if you look down in this space, this product is, well, there are 10 kilobits sort of in transit. All right, that's probably stuff that I can pipeline through and overlap communications with. But if you look up in these spaces, right, this is a megabit in flight, right? And keep looking, that's half a gigabit in flight in a wide area gigabit network. In fact, if you do these constants now, you'll see that these are sort of the amount of data in flight. It's actually easier as you get down to fewer, because you have to do less and less pipeline to accomplish it. Okay, so actually in this space, these things have nice qualities. That there isn't a lot that you actually have to concern yourself with keeping that pipeline full. So, okay. And I just said that this is sort of restatement, that the practical implication is that you can increase bandwidth. That might be good for non-interactive content, but if you talk about interactive content, bandwidth really doesn't do you much. Right. Okay, well, we saw this before. We do it, right? Disks, right? We had memory here and disks here. We had to bridge this gap before, and how did we do it? Right? Did disk caching, did overlap I/O. Right, so there's a theme here, by the way, as you see. Since I'm an architect, that's my hammer, everything's a nail. All right? Here's my problem. I'm going to take computer architecture and whack this thing with it. So what would I do as an architecture? I say, well, of course, I'll put caching in. Right? Then I want to replicate it. I want to take the content that's here and be able to replicate it out to these caches so that the bet is, right, that as I come up to my proxy, I want to get to that site, but I check this cache and it's there. All right, so classical caching. In fact, you do this bet that most of the requests are filled from that cache, and then you also get parallelism here at this level. If I miss, I go back to the site and load the cache. But if you also look at things like what marimba and push technology, you hear all about that. It really is just a way of with forcing forcing the contents of the cache to where you would like them to be, to update the caches sort of proactively rather than reactively. Right? And I think that's just how you push technology in this context. And so, cache sizes, fewer bigger ones are going to be easier to manage, and actually these proxies themselves will form caches. You have caches all the way down to your desktop system, and it really forms some sort of hierarchy here. So another big problem to go solve. But I would say that caching isn't enough, because it's great for sort of this context-free, more static stuff, but how do I get to these more interesting things? Okay, I want to do transactions, I want to do advertising and things that I don't necessarily want cached. Okay, so there I think actually I want to push more than just caching. I want to push functionality into the network that now is not just provided by the client, as we saw on the proxy side, but it's actually provided by the content provider to get the content to react and predict well in the network to a given level of service. Okay, so this is actually where I try to distribute that out. What are my advertising policies? What are the transaction architectures that I'm going to enforce? Okay. So let me close here with some more business questions. All right, I wonder about this, about how rich is this set of services? I gave you a very sort of specific motivation of something to help out with access of web content from poorly connected devices. But what's the business model for who runs them? I'd like to know. So here's my guess now, and again, speculating and thinking is very dangerous, because undoubtedly half of this is wrong. You have to figure out which half. I think that you'll have all of this stuff, the proxies and replication. I think you'll get messaging and conferencing, directory search, stuff, service locations. I think would be complete exponents. In other words, really people just outsourcing all of their relationships, external relationships. I mean, even internally. I mean, it may be, see, if this utility gets good enough, no, most companies, universities, they just want to go buy it, right? Buy it like you buy your phone system. Be done with it. Right? So the possible business model then is that you contract with these service providers. They provide their Java-based logic to get all this stuff to work, and you subscribe to some guaranteed level of service. Hard problem. Okay, please help me. How do I do this? And if you look at, you try to handicap who would be the dominant service provider. Here are all the things you better know. And I draw your attention to this one, because you better have an economic model to keep the capital investment going, or you're dead. And I think that it's really a synthesis of these areas. And we viewed these areas, telecom, datacom, and computing, as pretty distinct. All right? I would say Rutgers has this unique place of being in the middle of a lot of this, right? There's a very interesting juxtaposition here. And if you look loosely here, that there is things known here about circuit switching, and service levels and billing is really understood by this group of people. All right, so that's sort of what does it mean to make something predictable? They just aren't on internet time. It's my biggest frustration with this group. The datacom people are they know a lot about packet switching and these network connectivities, but they also tend to be the most purists of we are going to give you a packet contract and stuff it in, we'll deliver it. Okay, that has to break. And then sort of on the computing side, we talk a lot about how we scale up systems, and we know a lot about software development, but we don't pay so much attention to really the end-to-end issues in these scales. And so I think the prize of all of this is sort of the service and content fund that comes from that. All right, and I think it's going to make that $1 trillion a year in telecom services look small.